Okay, number 7 is g of t equals 1 plus t squared over the square root of t. And you're asked to find the general antiderivative of this function. So we'll call it capital G is what we're looking for. And to use what we learned last class, we have to be able to either recognize this off of one of our common antiderivatives, or we need to use the power rule, because that's pretty much all we have at this point. So I'm going to first recognize that I have the single denominator term, and I have multiple terms in the numerator, which allows me to split this up into 3 separate fractions as follows. Right? And then for each one of these, I can rewrite each one as a power of t. So the first one would be t to the negative 1/2. The next one would be, what's this? T over t to the 1/2 is t to the positive 1/2. And then t squared over t to the 1/2 would be t to the 3/2. So all I'm doing is properties of exponents, right? Subtracting the power up here, subtracting 1/2 from 1, subtracting 1/2 from 2. And now I can apply the power rule. So my antiderivative, capital G, I'll call it, of t, will be this first term. Antiderivative there is 1 over n plus 1. 1 over n plus 1, t to the n plus 1. And I do that for each one. So plus, let's try this one a little faster. 1 over n plus 1 would be 1 over 3/2, which is the same as 2/3. So this would become 2/3. T to the 1/2 plus 1 would have given us 3/2. So I'm doing that one quicker. Mentally, you might have to write it all down and take your time. That's okay. I'm going to do 1 over 3/2 plus 1. What's 3/2 plus 1? 5/2. The reciprocal of 5/2 is 2/5. So 2/5 t to the 5/2, and then plus our constant of integration. And then this one I need to clean up. That would just be what? 1 over 1/2, so 2 t to the 1/2. Plus the rest of that stuff. Okay, does that answer the question? All right, now let's take the quiz. So finish jotting down what you need there, and then we're going to take a quiz. You all ready? So make sure everything's cleared off your desk. I'll let you use your formula sheet if you've printed them out like I told you could. 1, 2, 3, 4, 5, 6, 7, 8. Yes. Today. It's due when you turn this in, bring up your take home. Okay, take one of these. Do not start yet. Do not start yet. Okay, part of, don't start, part of one of the things you're going to have to get good at in a class like this is the speed at which you can do something, all right? Meaning that when you get to the test and we have an hour 40 minutes for you to cover this material and do these problems, can you do that in that given amount of time? So part of the exam is, do you know this well enough that you can do this within that time frame? So you have 8 minutes. Go. 3 problems. It doesn't sound like a lot. Get to work, though. There's 3 problems, 2 on the front, 1 on the back. When you're done, bring up your stuff, please. Yeah, I was just asked that question. Let me address that, but let me first bring my little polling thing up here. Okay, first of all, let's take attendance, so please click in. Hold on, stop, don't do anything else. Okay, where's Spencer? Where's Spencer? Who's Spencer? Spencer here? How about Ernest? Okay, Ernest, click yours. Okay, I just want to make sure that something got off on the list, and I thought everyone got moved 1, but it looks like everyone's matched up still. Okay, go ahead, buzz in, click in. Anybody not on this list yet? Need a clicker still? Can you click his thing? Yeah, you did? Okay. All right, good, everyone's here. All right, now let's talk a little bit about this quiz. How many of you felt you did okay on that? Yes, yes, no? Yeah, how do you think you did? That's what I'm asking. All right. So I'm being asked, you know, are we going to have daily quizzes? And I do not like to have quizzes every day because we don't have time to use 20 minutes of class every day. We just don't have time for this. The point of me giving the quizzes in the beginning here is to try and get you to understand what it is that you need to know when you come into class the next time. That you can't just say, all right, well, you know, that made sense in class. I don't need to do the homework. So it's just to keep you on task. But at some point, you're on your own. I mean, I'm not going to quiz you all the time to make sure you're doing your homework and asking questions, right? Understand? But on the other hand, I could quiz you anytime. You could be any class. So just be prepared. That's all I can say. All right. The solutions to that quiz will be posted online, probably later on today. All right, I'll put those out there. And we are going to pick up where we left off now. Okay, thank you. Where did it go? So what were we talking about last class? Not that. The antiderivatives, right? We'd start talking about antiderivatives. And we had done a couple of examples. We had gotten, I believe, to, did we do this one? We did what? Yeah, we didn't finish it, but we got somewhere around here. So what I'd like to do is I'd like to do this part D of this problem, of this example, 4.7 example 1. So I'd like for us to try and find, if possible, the general antiderivative of little f of x equals 2 plus x squared over 1 plus x squared. All right, so the issue that we run into here is that it doesn't look exactly like any of our common antiderivatives that we're supposed to know off the table, although I will point out that 1 plus x squared in the bottom is related to which antiderivative? Arctangent, right? But the arctangent antiderivative has like a 1 up here. And we don't have that. We have a bunch of stuff. So I'm seeing that first. And then I'm also thinking powers of x, right? We've got a bunch of powers of x. But I cannot split that up like we did on that example that was asked in the beginning of class. We can't split it up because, why? we have 2 on the bottom, so it wouldn't work out as easily. Now, can we still split it, though? Yes. I could do this. I could do the 2 over the entire denominator, right? And then I could do plus the x squared over the entire denominator. That is a fair algebraic move, right? And then if I'm trying to find the antiderivative, I can try and do these separately. Now, the 2 up here can be factored out, so you could write it like this. 2 times 1 over 1 plus x squared. And that's because, just like with derivatives, when we took derivatives, constants in front of functions just followed us, followed the derivative. Same thing going backwards with antiderivative. If you have a constant in front of a function, take the antiderivative, it's just going to come with you. So I'm going to kind of ignore the 2 and ask myself, do I know the antiderivative of 1 over 1 plus x squared? Yes, it's arctangent, isn't it, of x. So I should be able to handle this first one. How about this one over here? You cannot do x squared over 1, x squared over x, right? Can't do that? Complete the square. Whoa, I'm hearing a bunch of different things. You can do what? What? 2x. Okay, I'm hearing a lot of different things. The one thing that I did hear that I liked was long division. That I did like. Because if you take this over here, I'll do it down here, and you take x squared and you divide it by 1 plus x squared, well, I'll switch the order. Then what would we get? Let's just try this out. What would I have to multiply x squared by to get x squared? 1, so I put a 1 here. And then I multiply 1 times this, and I get x squared plus 1. Then I come through and I subtract this line, don't I? This is old school long division here. And when I do that, what am I left with here? Negative 1. X squared plus 1 does not go into negative 1, so this is my remainder. So I'll write up here plus my remainder, negative 1 over x squared plus 1. That's the remainder over the divisor. So this expression here can replace this expression here. And then my question to you will be, can you do anything with that? All right. I'm going to do it this way. Minus 1 over x squared plus 1. Does everybody agree with this? Understand? This long division here becomes this. We already said we could do this one. What's the antiderivative of 1? X. What's the antiderivative of 1 over x squared plus 1? Arctangent of x, but this will be minus. This one was what, 2 times? So let's actually get our antiderivative now. Capital F of x will be 2 arctangents of x plus x minus what? Arctangent of x plus a constant. And I can combine like terms here, right? I have 2 arctans and take away 1 arctan, so that's just arctan of x plus x plus c. By the way, I'm just going to point out also, you could have done long division to begin the problem. You could have started this with long division, it would have worked. But I was trying to point out that this would be a fair algebra thing to do, and that one of the arctans is somewhat obvious in this case, right here. This one had to work for it a little bit. Yes? That's one you should know. Yes, arctan, absolutely. Now, the good thing about antiderivatives is that you can always check your answer, right? By taking the derivative. So I'm just going to take derivative of this real quick and see if we get back what we had. So what's the derivative of arctangent x? So I'm taking the derivative here. 1 over 1 plus x squared. Okay, plus what's the derivative of x? 1, and then what's the derivative of a constant? 0. So this right here is our answer. Does this match up to what we had up here? It doesn't look like it, but if you get a common denominator between these two, you would make this 1 turn into a 1 plus x squared over 1 plus x squared. That would be your 1, wouldn't it? And now combine these together, and what would you get? 2 plus x squared over 1 plus x squared, which is the original function. So that just checks that it worked, okay? All right, let's just make sure everyone's okay with that. Yay or nay? Are you all right? All right, good enough. The next note here has to do with linear motion, all right? Things moving in straight lines. So from Cal 1, hopefully you saw that if an object is moving in a straight line, if you know the position of the object at every point in time, we call that the position function, S of t, or S equals f of t, or position function, then the derivative of that, the first derivative of the position function, gives you the velocity function. So you know the position of an object moving in a straight line at every point in time, you can take the derivative to find its speed, or velocity at every point in time. You take the second derivative of the position function, and you have the acceleration function. So that's how the derivative works. Start with position, derivative is velocity, second derivative is acceleration. Well, here in Cal 2, if we're doing antiderivatives, we should be able to go backwards, right? Start with an acceleration function and recover the velocity function by taking the antiderivative, and then recover again the position from taking another antiderivative. So that's what this is saying. It's saying given an acceleration function, we go backwards to get velocity. Given the velocity, we go backwards to get position. But what's the problem when we go backwards? Antiderivative. What's the thing that we always have when we find the antiderivative? A constant, right? And we don't know what that constant is. So if we're going to be able to recover exactly where this object is or its velocity at every point in time, we're going to have to know a little bit more than just the function. We need more information. So what you're often given in a problem is the acceleration function, like this one. And then they give you what are called initial conditions, or some conditions. So I'm telling you, look, there's an object whose acceleration is 24t minus 6. And I didn't say if it's t is in seconds or anything. I haven't given you any units. Okay, so this is a very generic acceleration function. But I'm telling you, S of 1 is 7. What does that mean? The position after 1 second or minute or whatever our unit of time is 7 feet, miles, whatever our distance measurement is, right? So I'm telling you exactly where the object is at one point in time, right? And then I'm also telling you what? The velocity at a single point in time. If we have just that information, we should be able to recover everything. All right? Let's see how it works. So we're going to start off with an acceleration function of 24t minus 6. We are also given S of 1 is 7, and V of 1 is, it's V of 2, sorry. V of 2 is 41. And what you're asked to do first, part A, find the position function. So they want you to find S. That's the position function. Part B, they want S of 2. So what's the position of the object after 2 units of time? All right, so let's start with part A. How am I going to get back to position? I first have to go from acceleration back to velocity, right? So my velocity function should be the antiderivative of acceleration. What's the antiderivative of this right here? So 24 times 1/2 t squared minus 6t plus a constant, right? So I'm just using power rule on this, right? So my velocity function, watch how I write this. My velocity is a function of time. It is 12t squared minus 6t plus some constant. So I can tell you the velocity within a constant. So can you visualize the family of functions? Remember when I graphed the family of functions? Can you see that our answer for velocity can come from any family of these parabolas? Now we need to nail down exactly which one it is. And to do that, we're going to use that initial condition that was given right here, that my velocity at 2 should be 41. That means when I plug 2 in for t into that velocity function, it should spit out what value? 41. So that's what I'm going to do now. So I'm going to say here, but v of 2 must be equal to 41, which implies that when I plug 2 into this, so plugging 2 in, what would we get? 2 squared is 4, 48, so we get 48, take away 12, plus some constant I don't know, must be equal to 41. So just plugging 2 into this and saying that has to be equal to 41 allows me to solve for c, doesn't it? So 48 minus 12, 36. Yeah, so just move things around, you get 5, right? C is 5. All right, so now I can write the velocity function exactly as it is. So the velocity in terms of t is 12t squared minus 6t plus 5. That is my velocity function. Yes or no? Let me know. Yes or no? Okay. Am I done? No, I've only recovered velocity. I need to get back to position, so I'm just going to repeat this process again, right? Let's do that. So the position function, s of t, will be the antiderivative of this, which would give us 4t cubed minus 3t squared plus 5t plus a constant. Now, I did that one a little faster. I'm just expecting that everyone, given enough time, could do power rule on each of those. And now, same thing, right? But we know that s of 1 was 7, which implies that when we plug 1 in, what do we get when we plug in 1? 6 plus c must equal 7. We just plug 1 in for all your t's, and you get c is 1. So my position function, s of t, will be 4t cubed minus 3t squared plus 5t plus 1. That's what I wanted for part A, the exact position function. Now for part B, I just need to do what? Plug 2 into that, which I'm not going to do. Questions, comments, concerns, anything there? I would like to take a look at this and just do a slight variation of this. I'm not going to work through this whole thing, but I'm going to try and help you set it up. Okay, what if I gave you this information instead? I'm going to highlight in red the only difference in the problem. Can you see that that's red? It's kind of hard to pick up in here. Have I still given you an acceleration function? Yes. Have I given you 2 conditions? Yes? Well, Well, one is, in the last problem, is one was velocity information, the other one was position information. Here I've only given you what? Position information. Do you think you can still get it? So let's go backwards. We do the antiderivative. What was v of t? It was 12t squared minus 6t plus a constant, right? And then we used that initial condition to nail down what that constant was, didn't we? We don't have that information. So what I'm going to do now is just the only thing I can do, I'm going to integrate again. All right? So let's see, what's the antiderivative? So this is my position. What's the antiderivative of 12t squared? 4t cubed minus 3t squared. But now what's the antiderivative of a constant? C times the variable, ct. So this is plus whatever that constant was, which I didn't know, times t. And then our constant of integration, right, when we, constant, antiderivative constant, which is going to be, can't call it c, I'm call it d. Just use a different letter. Now, if I plug 1 into this, what should it spit out? 7. So plug 1 in real quick, what would you get? 1. So S of 1 must equal 7 means that what? 1 plus C plus D must equal 7. All right, I cannot solve for C or D here. I have one equation, two variables. But I have another piece of information, don't I? If I plug in 2, I should get 41. So what happens when I plug 2 in here? 2 cubed is 8. 8 times 4, 32, right? And then 2, 4. So take away 12. What do we have? 20 plus 2c plus d must be 41. And now what you have, and this is where I'll stop, you have a system of equations. You have two linear equations with two unknowns. You can solve this by either substitution or elimination or matrices or something like that. But it can be solved, right? And you can figure out what C and D are. All right, so I just wanted to show you that because, you know, the book or on a test or something, you might get the conditions where I give you a V and an A. V and S, position and velocity. Or you might just get two pieces of information on position. Could you solve the problem if I gave you two pieces of information on velocity? What do you think? Would that be enough, you think, or not? That'd be an interesting exercise to see if you could show whether or not that's true. Give you acceleration function and two pieces of information about its velocity. Can you recover the unique position function? I'll leave that as an open question for you. Anyone interested can go tackle that. All right, that's it for that section 4.7. That was the homework I had put up at the end of class last time. So on the question that you had asked, Tim, you asked, right? Number 19, you're just taking the antiderivative twice. Let's reserve that. If you want to talk about that, we can do it afterward or something. I know you want to go over that one, number 49. So let me address that. We've got, yeah, if I can give us 40 minutes, I'll be happy. I've been asked about page 190, what was it, was it hyperbolic? Number 48, yes. So what's the process, is that what you're saying? Okay, so this is the last problem I think I assigned. It gives you this differential equation, which we haven't really talked about. Probably you have not talked about differential equations. Okay, so it talks about how when you have cable hung between two poles, it takes the shape of some curve, and that curve satisfies this differential equation. So what the heck is a differential equation? A differential equation is an equation that has within the equation derivatives of a function. A very simple example of a differential equation is y equals y prime. That's a differential equation. Can you tell me a function, can you come up with, in your mind, a function of x that when you take its derivative, it's equal to the function itself? What? E to the x is an example of one, right? The constant zero function would work there too, but it's kind of trivial. So this is an example of a differential equation. You could have a differential equation that looked like this. Can you think of a function that when you take its derivative and you add to it its derivative squared, you get the original function? Maybe not. And that's why you study an entire class called differential equations, because you try and come up with ways to solve to figure out what these functions are that satisfy these equations. In this problem that's being asked, or that's being asked, you're asking me about this. They tell you this is the differential equation. They give you the function and they ask you to show it satisfies this. So first of all, what does this mean right here? Second derivative of the function equals two constants over a constant, square root of 1 plus this one, first derivative squared. And they say that's the differential equation. Show that this function t over cosine hyperbolic rho g x over t. Show that this satisfies this equation. So this is your f of x. This is, or your y if you'd like. This is your y. T, well, everything in here except x is a variable. Is a constant. X is your only variable. So what you need to do is take the second derivative of this and plug it in here. Take the first derivative, plug it in here, and square it, and show that this is equality. Got it? And when you do that, it's an exercise in algebra at that point. But this is a pretty neat problem to work through. It can be. I remember doing it a while back. So you just got to keep track of everything, right? All these constants. You don't have like quotient rule here or anything. These are all constants, so they just come with you as you take derivatives. In fact, you want to do the first derivative? I'll just do the first one. This stays the same because it's a constant. What's the derivative of cosine hyperbolic? Sine hyperbolic of what was in there, right? Times the derivative of what's in here, which is everything but x, right? Because x is like a variable. Everything here is a constant. Derivative of a constant in front of x is the constant. So we get this. Oh, wow. That cancels here and here and here and here. That's your first derivative. And then take your second derivative. And once you get your second derivative, put it here. First derivative here, square it, and then go to town. Okay. Is that enough? We good? All right. All right, now we are going to talk about the substitution rule. So up to this point, if we're trying to find antiderivatives, we have really two approaches. It's either something we remember the derivative from Cal 1, like the antiderivative of secant squared is tangent x, right? Because we know the derivative of tangent x is secant squared x. So it's either that sort of thing is happening, or it's a power rule, right? X to the n. And then we had one more, 1 over x. Antiderivative 1 over x was natural log x, right? So we have certain ones that we're going off of memory or we're going off of the formulas. The first method after that is what's called substitution, all right? And it's kind of like the idea you got to learn to crawl before you walk, right? This is going to be crawling, all right? We're going to have to learn how to crawl here. Substitution is our first approach, or our first attempt at getting on our feet. So before we do that, though, we need to get some notation down. Instead of me sitting there saying, hey, find me the general antiderivative of this function. Hey, find me the general antiderivative of this function. Keep on telling you that over and over. We have a symbol that we use for it. So if someone gives you a function, little f of x, and they want you to find the general antiderivative of it, they use this symbol right here. It is called the integral sign. It is an elongated S. It's an S that's been stretched out. And we will find out later, after we get through all the techniques of integration, that this elongated S comes from the idea that the antiderivative is very, very intimately connected with the sigma notation, the summation, all right? But not yet. We're not there. For now, we're just going to take it as a symbol and not ask him any questions, all right? So when you see that symbol, it says to you, find the general antiderivative. This whole thing, all of it together, is called the indefinite integral. Indefinite. Later on, it'll become the definite integral. There will be a difference between the two. But for us, it's called the indefinite integral. This is the integral sign. The function that is inside of this indefinite integral is called the integrand. Just like when you had something under a radical, it was called a radicand. Inside the integral sign, it is the integrand. The dx, the little dx that's right here, okay, is called the differential operator, or the differential. At this point, again, we're going to explore this later, all right? For now, just realize it's there. It keeps track of your variable. That's the way we'll look at it right now. Once we get to this sigma notation, you'll actually see that that dx has physical meaning, all right? So we're not going to worry yet. So when someone gives you this representation right here, the only thing that changes every time is this function in here, right? And then the dx is always there as long as the function had x in it. If the function was f of t, this would be dt. If it was f of m, it would be dm, all right? And so whenever someone says find the general antiderivative there on the left, you put your answer here plus a constant. Your answer is the capital F, the antiderivative. Notice what kind of went away here when you go from the left side to the right side. The integral sign's gone, right? When you find the antiderivative, integral sign's gone, and the dx is also gone. People always ask me, what happened to the dx? It goes away. When you take the antiderivative, it's not there anymore. All right. Capital F of x is called the antiderivative. C is called the constant of integration. The process of finding antiderivatives is called integration. So what we're doing now is integration. In Cal 1, you did differentiation. Cal 2, we do integration. Here's the rule that we've seen, right? That's that power rule. Remember that? We had the one exception if n was -1, and then I had said absolute value here, right? In fact, I think I'll throw that in there. We talked about the common things that you should know. Using on your page 6 of the formulas that you can print out for this class, formulas 1 through 20, you should know those so that when they do pop up, you're like, ah, yeah, I recognize that. That came off my formula sheet. All right, so this substitution technique that we're about to go through is what we use to try and undo the chain rule. So let's take a look at this example right here, and hopefully you'll see how undoing the chain rule is going to require a little bit of work. So we're starting out with, I'm going to give you a function, and I want us to take the derivative of it, all right? So find the derivative with respect to x of sine x squared, all right? So we're not doing integration right now, right? I want to find a derivative, Cal 1. So you have to use chain rule here. The derivative of sine of something is cosine of that, right? I don't touch the x squared yet. Times, now I go in, take derivative of the inner function, which is 2x. And then if I kind of rearrange things, I get 2x cos x squared. That's it. That's the derivative of that. So I say now, what is the antiderivative of x cosine x squared dx? So notice this part here, very similar to this part here, with the exception of what? I don't have a 2 there. So do you see the challenge? We need to go backwards from this back to that over there, or up there. We know it comes from sine of x squared, except we're off a little, right? We don't have that 2 there. How are we going to get there, right? How are we going to see this? So there's a standard sort of approach you can take, all right? And here it is. It's a general strategy. You look at the integrand, all right? You look in there. You try to find something. You identify something visually, and not only that something, you also see its derivative there, somewhere in the problem. Somewhere in the integrand, you see an expression and its derivative, both appearing in the integrand somewhere. It's important that the derivative of the something that you're looking at needs to appear in the numerator, not in the denominator. You'll see as we work through some examples. The derivative might be off by a constant. So if you're off by a constant, it's okay. What we'll do is once we've identified something and its derivative, we will make a substitution, which is why we call this substitution. That something that we saw, we will call it u. And then we see what happens. All right, that's the basic idea. Look for something in its derivative, replace that something with u, and then go to work. So let's begin with that one that I have right here. Start it brand new. Here's an example. I would like to know what the antiderivative of this is. Do you see something? Well, we should go back. Is this off of your table? Is this something you know the antiderivative of just looking at it? I mean, is it a common function? It's not one of your common ones. It's not the power rule, right? So it looks like maybe we should try substitution. So do you see something there and its derivative? X squared is the something that you see, and its derivative? The derivative of x squared is x, right? Now, derivative of x squared is 2x. We have what? X here? We're off by a constant, right? It's okay to be off by a constant. It's okay. We will adjust for that. So what we'll do is on the side here, here's where we're going to do our scratch work. We're going to make a substitution now. I said that you will replace whatever you saw, the x squared, with u. All right, so everywhere I see an x squared in the problem, I'll replace it with u. And now what we do is in our scratch work, we take the derivative on both sides of this equation with respect to x. Right, so what's the derivative of u with respect to x? We're going to call it du dx. So we're going to use Leibniz notation. And then on the right side, what's the derivative of x squared? 2x. That's it. Now, this ratio here, I'm going to remove the dx from the left side of the equation by multiplying both sides by that differential. So I'm going to multiply both sides by dx and get this. Everybody agree with that? All right. So this is taught so many different ways. I've seen this so many different ways. I mean, I do it my way. If you've seen something different, you know, you're just going to either have to adjust or just ignore me. I like to play a matching game, all right? What I do is I rewrite the integral, and I'm noticing that the x I have up here is right here. I notice that the dx I have here is right here. I don't have a 2 up here, right? So I need to get rid of this 2 on this side. So what I'll do is I'll divide both sides by 2, or multiply both sides by 1/2, and rewrite this line right here, so that I get this. 1/2 du is x dx. Now, some people have trouble with this highlighter stuff that I'm doing here. So instead, what I can do is just rewrite it like this. This is all multiplication between these three things, right? Between the x, the cosine x squared, and then the dx. So multiplication is commutative. You can slide things around, right? Move things around. And if I write it like this, it might be a little bit easier to see that this matches up exactly with this now, right? You'll see these two match. And then the x squared here matches up with this x squared here. So what I can do now is if I replace the x squared with u, this will become cosine u, won't it? If I replace the x dx with 1/2 du, then my entire integral has now changed from having x's in it to just u's, right? Making that substitution, my integral is transformed. So now I'm going to rewrite the integral. And I will use an arrow to represent I'm rewriting it. Not an equal, just because of what's coming later, okay? Just do an arrow. Whenever you make a substitution, change it. Change the integral's form to a different variable, just use an arrow. Cosine, what is this going to be? Cosine u. I don't need the parentheses anymore because it's not squared. And then what is this whole thing? Times 1/2 du. And this is great because this looks more manageable to me. If I take the 1/2 there, can I take it and just kind of pull it out and not even worry about it? Yes, because antiderivatives, it didn't matter, right? Right? Antiderivatives, it'll just follow us the whole time. So what we like to do is pull the 1/2 out of the integral completely and say it's 1/2 times whatever this integral is in here. Okay, let's take a quick vote. Are you okay up to this point? Remember, I'm shooting for an 80% okay. Anybody want to ask me a question? Okay. So now what we do is we just act like the whole problem started over, right? Forget about x for now. Someone gave you this. They're saying find the antiderivative of cosine of u, right? Where u is your variable. So kind of don't even worry about this right now. Just what's the antiderivative of cosine of u? Sine u, right? Sine u plus a constant. And then we have to have the 1/2 that's out front. Yes? So we have that this will be equal to 1/2 sine u plus a constant. So when I actually took the antiderivative from this step to this step, when I took the antiderivative, what went away? Integral sign went away, du went away, and the cosine u was replaced with its antiderivative, and I tacked a plus c on the outside. So are we there? Oh, go ahead. There's two answers to that. One of them is geometric, which I can't really explain yet because the way we're approaching this course is we're going to do all the techniques first, how you integrate, and then talk about where it all came from visually. So I can't explain it that way. The only other way to explain it is we're looking at du as really being like the derivative of x is 1, right? The derivative of x is 1. But we use the du to keep track of what our variable is. Because the original problem started with x, right? Now our problem is in terms of u. We need to somehow keep track of what variables are variable. So look at it as really being a 1 this whole time. It's just to keep us organized. That's the geometric explanation is much better, all right? Antiderivative of cosine. Antiderivative, right? The derivative of sine of u is cosine u. Are we done? No? I have to replace my u back, right? Look, the original problem was in terms of x. Your answer needs to be in terms of x. So what was u? Go back up here. U was x squared. So we put in equals 1/2 sine of x squared and then plus c. And we will box this up. This is our answer. And could you check it? Yes. Forget the 1/2. What was the derivative of sine of x squared? We did it earlier. It was 2x cosine x squared, and then put the 1/2 there, and that kills off that 2, so you just get x cosine x squared, which is the original problem. All right. Let me know if that all made sense or not to you. As you might imagine, these get more challenging. And then we learn more techniques, and this becomes the easiest technique. I know some of you can probably attest to that. It's, yes? Where? Here? Okay, all this was right here, this whole thing up here, was I was getting you to look at what's the derivative of sine of x squared. It's this. Okay, how would we go backwards and go from this back to this? And so I got us thinking, like, that's not as easy to do as we might think. So what do we do to do something like that? Well, we introduce this idea of substitution, looking for something in its derivative. Okay, let me do another one. How about find me the antiderivative of 1 over 2x plus 1 squared dx. We should always start by saying, can we do something we already know? Does that look like anything out of your common things? Like the arctan or no? The whole quantity is being squared, right? In arctan, it's just that one piece, x squared, right? 1 plus x squared. So this is the entire quantity is being squared. It's not the same. You could expand out the bottom, like FOIL it out, but then you'd have 1 divided by this quadratic. If you have 1 divided by a quadratic, can you rewrite each one as a power of x? No. You could do it if it were the other way around. So basically, after you've thought about this a little bit, you've exhausted all the other options, which brings you to substitution. Substitution says, can you find me something and its derivative there? Do you see something in its derivative? What do you see? What do you see? So you see 2x plus 1 squared. You can take the derivative of all this, yes, but do you see its derivative there? Does the derivative of this whole thing exist in the integrand somewhere? The derivative of 2x plus 1 does, but not the derivative of 2x plus 1 squared. Y'all see what I'm saying? I'm going to write it out, but if I just look at 2x plus 1, what is the derivative of 2x plus 1? It's just a constant. It's just 2. Do you have a 2 up here? Not really, but is it okay to be off by a constant? Yes, it is. So that looks like it's a good candidate. Now, do you understand why I don't want to pick the squared also? Because the derivative of that would be way complicated, and I don't see anything complicated like that in there. So I'm going to choose my u in this problem to be 2x plus 1. Yes, the derivative needs to be in the numerator. The derivative of this is what, 2? Is there a 2 up here? No, there's a 1, so I'm off by a constant, right? But it's in the numerator. You'll see, we'll do problems where you might think the derivative's there, but it's in the denominator, which doesn't work. Yep. Okay, so now I do that du dx is equal to, what did we say? 2. And then what did we do? Move that dx to the other side. At some point, very soon, I'm going to skip this step right here. I'm just going to go to du equals 2 dx. Like I'm going to move the dx over in my head right when I do, while I'm doing it. So I'm going to be able to replace this yellow with u, yes? I need to be able to replace my dx with something here. So what's dx over here? The dx is this. I need to get that 2 out of here. So 1/2 on both sides again. I hope you realize it's not always going to be 1/2 on both sides, all right? And now we should be able to rewrite the problem. Let's see what we would get if we rewrite this. Integral 1 divided by u squared, and then what's dx? 1/2 du. And what am I going to do with that 1/2? Take it completely out. It is multiplication, but I'm not going to write the multiplication here. It's implied. And then what is 1 over u squared? That's u to the negative 2, isn't it? That's a power rule. I can do a power rule on that. You see? Because it's just u to a power. So I can bring it up and do power rule. Are you all clear that you could not have just rewritten this as 2x plus 1 to the negative 2 and done power rule? Because you've got 2x plus 1 is more complicated than just x, or in this case, than just u. U by itself, 1 over u squared is just u to the negative 2. 1 over 2x plus 1 squared is a lot more complicated when you expand that all out. Hope that makes sense. Questions? All right, what's the antiderivative of u to the negative 2? So it'll be 1 over negative 2 plus 1 u to the negative 2 plus 1 plus a constant. So this is negative 1, right? Right here. So times this is going to be negative 1/2 u to the negative 1 plus a constant. What is u to the negative 1? It's the same as 1 over u, right? So I'm going to rewrite this as 1 over, negative 1 over 2u plus a constant. By the way, you could leave it as u to the negative 1. That would be fine. But you do need to do one more thing. What is it? Back substitute u. So you need to plug u back in, right? Your answer needs to be in terms of x. So we would have negative 1 over 2, and then what was that, u? 2x plus 1 to the first power down there, and then plus c. Could you distribute that 2 through the bottom? Yes. Do you have to? No. I'll point out again, I'll get your question just a second. I'll point out again, this step right here, when we did the integral down to here, the integral sign went away, the u disappeared. Yes, whoever said. Where? This? No, because this u to the negative 1 comes down as u to the positive 1. It's not multiplication. You're not multiplying numbers here. Are you saying with this number here? The negative? Is that what you're talking about? Oh, no, I'm not taking a derivative. I'm not doing anything to this. This is just rewriting algebraically. What does u to the negative 1 mean? 1 over u. I didn't take a derivative or antiderivative or anything. Any other questions? Whoa. That was weird. Okay, let's try another one. You're not going to have problems like that on the test. Yeah. this is just warm up. You know, we're just getting used to this right now. You wouldn't have something, I think, that you could do U sub that quickly. Maybe, I don't know. U sub will appear somewhere within the integral. What I should point out, remember what I said the first test is over? Integration. The techniques of integration are as follows. U substitution, that's what we're doing now. Integration by parts, okay, is the next one. Then you have trig integrals, trig integration. Then you have trigonometric substitution. Then you have partial fraction decomposition. Okay, those are the 5 basic methods for integration. The challenge of exam 1 is that when you're presented with an integral, you are not prompted as to which technique to use. That's the challenge. So you wouldn't have a problem like this because this is so early on still. But if it happened to, yeah, do it mentally if you can do it mentally. Like some people can look at this, maybe 1/4 x to the 4th plus 7 raised to the 11th plus c. Maybe you're there. Maybe that's you already and you're good with that. And good. But that takes time, right? Practice. And so here we go. What do you got? How about power rule? Hold on, power rule. I could multiply this out. I could multiply x to the 4th plus 7 to the 10th power. I could do 10 of them, multiply them all out, right? And then distribute an x cubed through and do power rule on each one, right? I could do that. I'm not liking this u sub, so I think I'm going to do that. So I'll just change it to 100 power, and then I'll make you surrender. You surrender yet? Right? Okay. You see what I'm saying? Like, there's a good reason why we use substitution. It can help us. So we'll do 100 power, right? Everyone change that to 100. So do you see something in its derivative? I think I already heard it. X to the 4th plus 7. You see its derivative, kind of? Okay, so let me try this. U is equal to x to the 4th plus 7. The derivative of this would be, what did you say? 4x cubed dx. Now, do you see on this time I did not show that middle step? I just went straight to du equals 4x cubed dx. I'm going to rearrange the integral only to help people see this. We have x to the 4th plus 7 to the 100th power times x cubed dx. I'm doing that to focus your attention on the x cubed dx as appearing right here, right? I've got the x cubed dx right there. If I can just isolate it over there, so I should multiply both sides over there by what? 1/4? Okay, let me give a quick snapshot of how everyone feels. Give me yes or no so far. I need to figure out who that 4% is. It's on you to come to me, all right? If you're having any trouble with this. All right, I'm replacing the x to the 4th plus 7 with u, right? The blue part's going to be replaced with what? This blue part will be replaced with 1/4 du. So we should be able to roll here. This is going to become a new integral, u to the 100th power, then our 1/4, what? Du. I like that. The 1/4 comes out. U to the 100th power, du. U to the 100th power is something that I feel, hopefully you feel comfortable with. Power rule on this. Antiderivative of u to the 100 is 1/101 u to the 101. But then I have a 1/4 out there. So that would be 1/4, 1 over 101, u to the 101, plus my constant. Final answer, final answer. 1 over, what? 404, final answer. X to the 4th plus 7, that's my u, to the 101 plus c. There you go. How do you think you're going to get good at this? Practice, right? You're going to have to do a lot of problems to get good at this. And like I said, the good news is when you do your homework, you kind of know what you're supposed to be doing here, substitution, right? I mean, you know that. So take advantage of that now and work through as many problems as you can. What's the general antiderivative of sine 2 over x, all of that over x squared dx? So after going through your process of that doesn't look like a common formula. Oh, wait, hold on. How about this as an answer? You're me, you're grading this. Out of 10 points, what do you think? Out of 10 points, how many should I give this student? 0 being nothing, 10 being everything. Can you see what they did? What did they do? The antiderivative of sine is negative cosine. They knew that much, so they just wrote that. And then the antiderivative of x squared is 1/3 x cubed. They added the constant of integration. But this is, again, a fundamental problem, right? This is, yeah, you get a sticker. What's that? Yeah, I didn't even address that, right? But even more fundamentally, you do not do the antiderivative of a quotient by just doing the antiderivative of top and bottom. Cal 2 would be so much easier if that's the way it was, really. It would be like in Cal 1 if they said that the product rule was just multiply the two derivatives together. That's what it would be like, but that's not the way it is, right? So this, to me, I mean, that's like 1 to 2 points out of 10. I mean, and that's on a good day. You remembered C. You know the antiderivative of x squared. But that's a big, so I only bring that up not to make light of it, but I mean, I see that stuff. I see that. That shows me not even that a student probably didn't even do the homework where they were checking their answers in the back to know, like, I'm way off on these, you know? Okay, so let's get back to this. All the other things kind of go away. You can't figure out, all right, substitution. Do you see something in its derivative? Anybody? Okay, how though? You need to see something and then its derivative. Tell me which is the something. 2 what? 2 over x? You want that to be the something? Okay. Let's try it. 2 over x. And you're going to need to take derivative of that, right? So before you take derivative, rewrite that as 2x to the negative 1. It's easier to take derivative of it that way, right? You could do quotient rule, but who wants to do that? What is the derivative of 2x to the negative 1? The derivative, not antiderivative. So it's du is negative 2x to the negative 2 dx. So the negative 1 came out, made it negative 2. Subtract 1 from the power, and what do you know? Oops. What is negative 2 over x squared dx, right? Okay. Do you think we have that over here? Do we have that derivative over here somewhere? I'm off. You've got to be able to see that though, right? So let me see if you can see this. I'll peel this fraction apart. This is sine 2 over x times 1 over x squared dx. This and this are the same exact thing, right? You slide the sine of 2 over x to the side, you're left with the 1 on top, you just split it off. So do we have something in its derivative? Here's the something, right? The 2 over x, its derivative is this. Is this right here? Not quite, right? I'm off by a constant, right? So what should I do to make this over here a 1 over x squared dx? Divide both sides by negative 2 or multiply by negative 1/2, either way. So back here, I'm going to go negative 1/2 du equals, when I do that on this side, I get 1 over x squared dx. So this matches this now. And this was my u. I divided by negative 2. That's what I did on both sides here. Divide both sides by negative 2, which is the same as multiplying by negative 1/2. Let's take a quick poll. Yes or no? I have some students in here who had me for Cal 1, and one of the biggest pieces of advice that I gave them coming in here was you need to be good at derivatives to do good at this, because, like, for example, what was your name, sir? Jake? Okay. Jake was the one who recommended 2 over x. I'm assuming Jake saw 2x to the negative 1, because that's what you said, and Jake knew that the derivative of 2x to the negative 1 would produce the x squared in the denominator that we needed. The only way he knows that is if he's done enough differentiation to have that almost automatic, right? So if the Cal 1 is still a struggle, if you're still having issues with exponents, oh wow, 2 over x, yeah, I completely forgot that that's 2x to the negative 1. Like, if that's still a big stretch, it'll continue to be a challenge. So we want to keep practice till that stuff becomes just second nature to us. So it's hard to teach this stuff because a lot of it becomes instinctual at some point. All right, let's rewrite the problem. Integral, what? Sine u times negative half du, and I pull the negative half out. What is the antiderivative of sine of u? Negative cosine of u. So when I make this a negative cosine u here, and then I hit it with a negative 1/2, the negative and negative becomes positive, and so I get plus 1/2 cosine u plus a constant. And then final step, substitute in the u. U is 2 over x, and we're there. We could always check, right? Box it up, and we move on. Okay, I've got like 5 or 6 more I want to do, but we only have about 12 minutes, so but this one. E to the x over I'll keep it nice. 1 plus 9 e to the 2x dx. One of the big rules of thumb in this class, when you're doing integration, is to keep trying. You have to try something, okay? If you're just sitting there looking at it and you're like, I just don't see it, you don't see it. If you're not writing anything down, you're not trying. You have to just make a substitution. Go for it, right? You're going to fail more times than you succeed in this class, so just get used to it, you know? Well, you know what I mean. It's like riding a bike. You know, when you first learn how to ride a bike, you're gonna well, some people just get on, they're like doing jumps already. But it's an analogy. I'm trying to make an analogy here, right? Be prepared to get some bruised knees, all right, or roughed up elbows. It's going to happen here. It's the only way to get good at it. It's like those guys on the X Games that want to practice new tricks on their bikes and motorcycles. What do? They jump into a what? A foam pit. Why don't they just do it? Why aren't they badasses? Why don't they just do it, man? Right? Because you're going to fail. You're going to mess up. You know, you're going to try something harder than you're used to. You got to be prepared to like not pull it off the first few times. All right? And I think that leads to a bigger issue of why you're here, right? And a course like this is designed to identify the people who can meet the challenge of this. Because that's who you want to go build the bridge. You don't want to be the person building the bridge and be like, nah, this looks too tough, man. It's too tough, man. I don't think I'm going to be able to figure this out. So take a swing. All right, you've had time. I've been commenting here, giving you some time to think through this one. Someone give me a bat to swing here, right? I'll swing it, but give me something. You want the whole denominator? All right. It's not going to work, but let's do it. How do I know it's not going to work? Because I've taken enough swings at these, all right? And that's the way, I mean, you want to get to that point where you have taken enough swings that you know what to do. And we were talking about timing the quiz, right? When you get to that first test, if you take 20 minutes to figure out the correct bat to use, that's part of you not being prepared yet. All right, so why isn't this going to work? Well, when I take the derivative of 1 is 0. The derivative of 9 times this. So the 9 will just stay there. The derivative of e to something is e to that something. But then chain rule says the derivative of what was up there was what? 2, and then I throw that dx on the outside, right? And then du equals, let me just clean it, 18e to the 2x dx. If you did this, you're saying you want me to replace this right here with my u, right? So that's going to be taken care of. The question is, what remains there, is that your derivative over here, is it up there? Why not? I see an e. This is e to the x, this is e to the 2x. It's not the same thing, right? We do know that e to the x squared is e to the 2x, but e to the x is not the same as e to the 2x. So they don't match, do they? Now, maybe you could tweak it or something, but right off the bat, I'm thinking they don't match. I want them to match. Yes? But in this, what I did gain is this, that I can always replace e to the 2x with e to the x squared. So let me start this over. I'm gonna say, good try. Go get a Band-Aid. Do y'all want a medal for trying? Do you want me to give you a first place ribbon for trying? Or do you want a first place ribbon for being in first place? You know what I'm saying? Yeah. Yeah. I'm making a comment on the way things are these days, right? Nobody can fail. Everybody gets the ribbon. I better shut up. Let me see. Okay. I know I'm recording, and that's why I better shut up. Okay, so I'm going to instead rewrite this down here as squared, but I have that 9 there. So I'd need to put a 3 if I'm going to square the whole thing, right? I would need that, wouldn't I? Now take another look at this. If that's the same expression, what could you possibly use for u this time? 3e to the x, right? What's the derivative of 3e to the x? 3e to the x. Do you have 3e to the x up there? You're off by a constant. Do you see that? That's you. I don't know. Do you see that? Okay, so I'm going to make u be equal to 3e to the x. The derivative of this will be exactly itself, dx. Don't forget that dx over here. Why is that dx so important? Because the way I'm teaching this is that you're playing a matching game. So if you get the dx, you're never going to match. I'm also going to rewrite the integral. I used to never rewrite the integral, but last semester I had a student who, first time I met with this student, I was like, there's just no way this person's going to get through this class. And they were so damn persistent, they just kept at it and kept at it. I mean, the true definition of effort. And they passed this class with a C, a good C, you know, like a well-earned C. But I mean, I had to pull this stuff apart for them to see these things. And if that's what it takes, I'll show it. I don't care. All right, so what do we have here? I pulled this e to the x dx on the outside like this, left a 1 up here, and now I'm going to match. I've got my e to the x dx here, got my e to the x dx here. It's kind of like a puzzle, isn't it? It's like a game. Yeah, we have the e to the x dx here, e to the x dx here. I need to get rid of that 3. So 1/3 on both sides there. Can't believe I only have 4 minutes left. Well, I have to show you. If I didn't have to show you, it'd be a lot faster. Okay, are we good? Are we matched up exactly here now? Let's rewrite it. What do we got? 1 over 1 plus u squared times 1/3 du. I'm going to stop putting those constants in there because they keep on coming out, don't they? So I'm just going to put them out there now. Put my du out here. Arctan. That's arctan. Arctan of u, right? It's arctan of u, not arctan of x, because our variable is u. So the antiderivative, this is one we had to recognize. Arctan of u plus a constant. But what was u? 3 to the x. Unfortunately, we're going to have to end on this one. But let's talk a little bit about this result. Let's talk about this result. The original problem right here. it might be pretty challenging to think that that antiderivative would ever involve an arctangent, but it does, right? It does. So I think we've come quite a ways here with this one. There's still some more problems in this section that are a little more challenging than this. Well, yeah. So I did get to do about 4 or 5 examples that I wanted to do. We'll do those next class, which is on Monday. Wow, we have the whole weekend. Why don't you try for your homework, see what I've gotten here. I didn't put the homework assignment here, so I'll just write it down. For your homework, this is section 5.5. I don't know what page it is. Numbers 1 through 36, all of them. So I would start with the odds, work your way through all the odds, then go through the evens, because the odds, the answers are in the back of the book. I have the complete solution manual in my office. If you ever come by my office and you want to come and look at them, I'll be happy to let you sit there and look at the, they're kind of worked out. Pardon me? I may have some of these solutions. I don't know if I have them all. Yeah. Okay, don't forget to turn in your clickers. Do your homework. Have fun. Good luck. Go Cowboys. Super Bowl weekend, right? Oh, wait. Hold on. Wrong way.